Okay, welcome to section 5.6, areas between curves. So what we already did is we looked to find the areas under a function. In other words, really, what specifically was said, we want to find the area between some function f of x and the x-axis in between two values, a and b. Now, what we specifically were looking at is really functions that were positive. So in other words, their graphs were above the x-axis. So when I find the integral from a to b of f of x dx, what I'm really finding is the area between the function f of x graph and the x-axis. Yes, so it's this positive quantity. Now the thing is, that's really the same way as looking at what? The area between these two curves. From a to b of f of x minus this function here. What is this function? This is a constant function. What is the equation of the x-axis? The equation of the x-axis, being a horizontal line, is that y equals to 0. So what I'm looking is really the area between what? The function f of x, which is above, and the x-axis, which is below. So the equation of this graph is y equals to 0. So in other words, 0, right? So we take whatever this equation is minus 0. That's of course the same thing, yes? So the reason why I'm bringing this up is because we're looking now at areas between curves. So if I should have a function actually, let me look at that dips below the x-axis, what's going to happen? What if a function becomes negative on some interval a to b? And again, I want to find the area from a to b, and it doesn't matter if a and b are positive or negatives, but if I'm looking at that, really this would be a positive quantity. This down here would be a negative quantity. Let me do this. So this part here is positive. This part here is positive. But this part down here will be a negative value, yes? Because all the accumulation is negative y values, right? So remember, what's the area is the heights, right? So the function value times this distance here, the function value times this distance here. When these are positive, those are positive values. These distances, these width of intervals are positive. However, what? The y values here are negative. So that's going to be a negative amount. So if you have this amount, this is a negative and this is a positive again, they really would cancel each other out. So they wouldn't truly give you the area under the curve. This part will be canceling out the other part. So if I want the area under the curve, really what I need to do is basically take the absolute value of the function f of x. But one other way of looking at it is really that what am I doing? I'm trying to figure out where does it dip below the x-axis. So I'm looking, let's say these are some values c and d, and let's say I'm looking, well, from a to c, the function is above the x-axis, yes? Between c and d, what happens? The x-axis is above the function. And then between d and b, the function is again above the x-axis. So sure enough, that's really the same thing as looking at what? You're looking and finding the integral of the function f of x as long as it's above, but when it's below on that interval, what do you have to do? Take the opposite of it, right? Make it positive again, okay? So that's if we compare a function really to the x-axis. So what I'm trying to say is that if you truly want to find the area under the curve, the part of a function that dips below the x-axis has to be taken as an opposite. So you need to make it positive again. As I just said, what you really have to do, anything that's positive stays the same. Anything that's negative has to change signs. It has to be made back positive. Yes, so basically that's what an absolute value of a function does, right? Makes every part of it positive. Now, what we're looking at is areas between curves. So it doesn't have to be about the function in the x-axis. It could be any two functions. So let me graph two functions here for you. And let's say here's a function f of x. And let's say here's a function g of x. And we're going to cut this on some specific interval from a to b, right? And we want to find the area in between. Well, to find the area between these two curves simply means to find the space, right? That's the area between them. Now, an easy way to figure this out, and let me write it down. So the area between the graphs of f of x and g of x on a specific interval from a to b. I'm not even stretching out these functions going past. I just want to know what happens. See, it's cut on all parts. It's cut vertically, it's cut horizontally by these two functions. Now, sure enough, that's not some kind of nice rectangle that I'd know how to find the area of. But exactly as we said, who is there to help us find areas of weird shapes? Well, that's going to be an integral. So it's going to be the integral from a to b, and this is how simple we're going to make this be. What do I have to do? I have to take the area from f of x all the way down to the x-axis. Well, that's f of x dx minus what I'm subtracting is this little gap, yes, which is really the area under the function g between a and b. So just as I had subtracted the x-axis before, it totally makes sense. If you want to find the area in between, what do we have to do? And again, we can take the integral of a sum or a difference. We split up the integrals, so we might as well put it together under one integral symbol. There it is. And the reason for why this might be very helpful is because imagine this is some kind of polynomial, this is some polynomial. When you subtract them, you get to cancel or combine like terms, yes? And you make your polynomial shorter, right? Your resulting function shorter. So that makes total sense that that's how we would do it, right? Find the area between the curves, take the function f of x minus the function g of x. Now, why wouldn't I go g of x minus f of x? Clearly, because as I see, these are the higher y values, right? This is the function above. When I subtract from something more, something less, it's going to stay positive, yes? Now, if I were to give you two equations, which I will in a minute, how do you even know which one's the above function and which one's the below function? The second issue I have, what if they swap? What if they cross in between, yes? So these are the issues that we need to look at. So I'm going to write this down. Make sure that you always subtract the lower function or the lower graph, yes, the function with the lower graph, from the higher function. In other words, the one that has higher values. So we have three situations. Okay, all right. So we have three situations here. What we're going to do is, I'm going to write this down. This pencil. Okay, here it is. So, situation one. What if I am given, these are the three types that we are going to ask you to find. So, again, to find the area between some function f of x and g of x on a specific interval a, b, right, with g of x, f of x, it wouldn't have mattered. But here, let's say f of x is always greater than g of x on the whole interval. So that's easy. That's just what we had, right? So the function f of x is always above. The function g of x is always below. On what? Even if this is stretching, and they might not do so, but on this interval a, b, that's the case, right? So to find the area makes total sense. You're going to take the integral from a to b, and you're going to take the above function minus the below function, and there you go. That's what's going to give you the area. Second of all, what if what? We want to find the area again between f of x and g of x on some interval a, b, and we're giving you the interval, but the functions cross. So let me draw a better picture of this. What does it mean the functions cross? Here's a function f of x, and here's the function g of x. And I wanted to find what? The integral, or I should say the area between them from some a to some b. And they actually could cross several times in between. I'm just making them have one crossing point, but they could have weaved up and down several times. So to find the area between f of x and g of x from this interval a to b means simply to find what? Which specific area are we looking for? And clearly, it would be this piece up here and this piece down here. That's the trapped area, right? It's between these two graphs, and it's crossed by A, or cut by A and B. So, as you see, because they're crossing, it's not this space down here, right? It's just the space trapped between the two graphs, between these two vertical lines. So as you see, what happens? They're crossing, right? So let's say this crossing point is some value C. And as I said, they could have crossed several times. And I can draw a picture for you. So how am I going to find the area? I'm going to have to, in fact, find that crossing point. And then the area between these graphs is going to be what? Well, from A to C, which one's the above function? Between A and C, G is above f of x. And then from what to what? From C to B, f is above g of x. So I have to always make sure that I'm taking away from more, less, or less from more. So the above function has to be before minus the lower function to ensure that the area stays positive, right? Does that make sense? So let me just doodle really quick here. What would have happened if I have a function, if I have two functions that interchange a few times? And I want to find the area from A to B. Then what happens? Between A and B, this function's crossing twice. Yes. So we'll call this some C value and some D value. Even though, see how F is dipping below here, it's not going to be a big deal below the x-axis. So what happens from A to C? Well, from A to C, let's say this was my f of x, the red one was my f of x, and the green one, again, was my g of x. Between A and C, who is above and who is below? Between A and C, F is below G. I'm sorry, F is above G, right? From what to what? From C to D. And I know I'm supposed to put a dx, but I'm just trying to make this informally. From C to D, who is above G is above F. Okay, and then from what? From D to B, who is above? F is again above G, right? So you have to interchange them, right? And now what I was saying before is that even though f of x goes below the x-axis, that's not going to be negative. Why? Because I'm minusing f of x, right? So all these negative values are going to become positive anyhow. So it takes care of that, the subtraction part. Okay. Now, a third situation is when we simply ask you to find the area between two curves, but we give you, so just say find the area between two functions f and g. That's it. No limits of integration. No interval. So what does that mean to find the area between them? Well, that simply means that these two functions must be trapping some sort of area in between them. So let me draw a picture for you to show you. What we will do a lot is we're going to cross parabolas. So if I look at these two functions, f of x and g of x, and I'm not giving you any limits of integration, what do you think it would mean to find the area between them? Is there some trapped space between these two curves? And sure enough, that's what it is. That's the trapped space between them. Yes. Right? This is going to be open. They're not going to meet again. So in other words, what's going to happen is that your limits of integration will have to be the intersection points. I'm going to make it even more clear. It's going to be not the intersection. A point has two coordinates, right? Which one do you grab? So it's going to be the x values where what? F of x is equal to g of x. So to find the intersection points, we just have to set them equal to each other. And what we're grabbing are the two x values, yes, where the two graphs meet. I don't really care the heights of them. I care about, again, the a and b values are always x values, right? Between these two x values, that's vertical lines that we cut them in between. So this is going to become your a, and this is going to become your b, okay? Now, what if they cross multiple times? No problem. That's, so again, once you found that intersection point, so we'll have to find the intersection points. Now, we will have to find the intersection points even for curves that cross. So graphing will really kind of be very important in these problems, okay? So once we find the intersection points, those are going to be our limits of integrations, right? Our a and b. What I was saying is, what if the functions cross multiple times? No problem. And I'm asking again just to trap them. So here's some function f of x. Here's some function g of x. And we want to find simply the area between them. There is no limits of integration given. We could say, hey, here are two functions, find the area from this to this value, right? Then we know where to cut them. But if we don't say where you're supposed to cut them, then clearly what we mean is they're going to cut themselves. And what we're simply looking at is the intersection points, and that's the part that we're taking, right? So let's say that's your A, that's some kind of B, and that's some kind of C value right here. Yes, so we found the three intersection points. Maybe there's more. Yep, of course, we're not going to go nuts in this class, but I'm just saying. 2 intersection points, 5 intersection points, it's the same concept. So again, what will you have to do? You will have to have 2 separate integrals, right? From A to B, and then again from B to C. And then you're going to have to look at what? From A to B, who is the above function? Well, the red one, that's F. And from from B to C, which one's the above function? That's the G. So you always need to make sure you take, or you subtract the higher function minus the lower one. And you need to know how to find them. So that's the next big question. How would we know without graphing, which function is above and which one is below. So that's the big question. If I'm not in the mood to graph them, sure enough, at home you can put these functions in Desmos. If you have a graphing calculator, you're welcome to use it. But let's say you have none, right? And you want to know, well, I'm not in the mood to graph them. How do I know which function's above and which one's below? Easy. Just pick a test point and plug it into both functions. Something's crappy. Into both functions. Whatever. Into both functions. What does that mean? Let's say this is some -3, and this is a 4, and this is a 7. Yes. And I know they cross. I set the two functions equal to each other, and they crossed at these values. Now, which one? How do I know which one's above and which one's below? Just pick a number between -3 and 4. Yes. Well, obviously 0 is easy to pick. Plug it into both function, whichever gives you the highest number. Well, that's the function above. Yes. Pick a number from 4 to 7. Let's say 5. Plug it into both functions. Yes. Which one's the function above, or which one gives you the higher value? That's the function above. So that's that. Now it's time to do some problems, right? Say, okay. So here it is. And we will tell you functions that cross or functions that don't cross, so you don't have to. In other words, we'll tell you if you have to find intersection points. So here it is. Find the area between f of x is x squared plus 5 and g of x is equal to 2x plus 3 on the interval from 0 to 3. Okay. So I'm going to graph these for you because this is an easy one. So 2x plus 3 is nothing but a line. That starts on the y-axis at 3. The slope is 2 over 1, right? So we're going 2 up, 1 to the right, okay? The second one, the function f of x, is a quadratic function, x squared plus 5. So it's a quadratic function that got moved 5 units up. And the quadratic goes up way faster than the line, so it's going, starts above and it's going to stay that way. Okay, so all we have to do is find the area between what and what? 0 and 3. Okay, so there it is. That's the space, the trapped space, right? So I'm making that. So it is clear to us that which one was the above function? It was f of x. And it was clear to us from the graph, yes? You can put, as I was saying earlier, if you want to know, you can put in point into both. So you could even put 0, right? If you plug into 0 into both, see how this is more than that? You can plug in a 3. 3 squared plus 5 is 14. 2 times 3 plus 3, that's not going to be past 14. So f of x is still above g of x. Okay. So I'm going to take the integral from 0 to 3 of x squared plus 5 minus 2x plus 3. And now, as always, do not forget to distribute in the minus sign. That's a big common mistake. So integral from 0 to 3. So it's going to be x squared minus 2x, and then 5 minus 3 is a positive 2. Okay. So the antiderivatives of this is x to the third over 3 minus 2x squared over 2 plus 2x evaluated between 0 and 3. Okay. So plug in the 3 value, plug in the 0 value. And I plug in 3, that's going to be a 27 over 3. These go away, by the way. Minus 9 plus 2 times 3 is 6. And all these are just a bunch of zeros. So now the answer is 6, right? That's a 9, right? 9 minus 9 is 0 plus 6. So you're trapping exactly 6 square units between these two graphs. Okay, so I'm going to stop this video and we're going to continue on a second one.